So today we're going to be going over our angle sum formulas for sine, cosine, and tangent and seeing some applications of those. So first of all, what we're talking about is something like this. If I have sine of A plus B for two different angles, A and B, or maybe even the same angle, then it turns out that this is equal to sine of A times cosine of B plus cosine of A times sine of B. Well, then very similarly, we have the angle difference formula, which is almost the exact same thing. The only difference is that we have a minus here in the middle. Well, then we have our angle sum for cosine. Cosine of A plus B is cosine of A times cosine of B minus sine of A times sine of B. Then cosine's angle difference, cosine of, well, that erased much more than I intended. Cosine of A plus B, sorry, difference. Cosine of A minus B is almost the same, but again, we just changed the sign there, and the rest stays the same. And then for tangent, we have tangent of A plus B is equal to tangent of A plus tangent of B divided by 1 minus tangent of A times tangent of B. And then tangent's difference, just like the others, all that changes is instead of adding up here, we're going to subtract. And instead of subtracting down here, we're going to add. And like I've mentioned before, really there's nothing stopping you from using the angle sum always and just pretending the angle differences don't exist. It's just you're plugging in a negative on the inside there. It's just the angle difference formulas are just saving you a little bit of work so that everything is suddenly a positive angle that you're working with. But the process would still be the exact same. And again, we have notes that we get to bring into the exams, so don't try and necessarily maybe memorize all of these as much as just make sure that you have written down what you need to in order to answer these kinds of questions. So, what kinds of questions do we get asked? Well, we may have something like sine of, I'm trying to think of something that's not a basic angle. Sine of, let's say, 15 degrees is one that we did in class. Well, I don't see 15 degrees on the unit circle. I don't have a table anywhere telling me what sine of 15 degrees is supposed to be. But I can rewrite this 15 degrees as 45 minus 30 degrees. Why did I pick those two numbers? Well, I happen to know exactly what the angles are for 45 and 30. And my angle difference formula lets me rewrite this as something just in terms of sine of 45. Sine and cosine of 45 and sine of cosine of 30. Sorry, yep. So sine of 45 times cosine of 30 minus cosine of 45 times sine of 30. Well, then I know what sine of 45 degrees is. It's root 2 over 2. So we have root 2 over 2 times cosine of 30 degrees is root 3 over 2, minus cosine of 45 is root 2 over 2, times sine of 30 is 1/2. Very good. And this is as far as we really like to take these kinds of questions. Sure, I can simplify this, and sometimes it does help us see things, but generally speaking, you don't have to show any more, because any of the rest of the work that we did is just adding, subtracting, fractions, all that mess, which I am not testing you over. We're not testing you over that kind of thing here. So once you get to right here, that's as far as we ask of you to do. Okay. So again, the general process was I may have not known what the sine of 15 degrees was, but I can look at 15 degrees as this difference between those special angles that I do know how they evaluate to. So that's what those basic questions end up looking like. Well, what if we have a kind of question where instead of you know exactly what the angle is supposed to be, I tell you cosine of alpha is 1/2, and sine of beta is 3/4, then I may ask you to find sine of alpha plus beta. So we may not know what the angles alpha and beta are, but I do know that cosine of that alpha evaluates to 1/2 and sine of beta evaluates to 3/4. Well, first of all, I may not know exactly what alpha and beta are, but I can just look at my formula to see what this should evaluate to. Well, that should be sine of alpha times cosine of beta plus cosine of alpha times sine of beta. Well, there's a couple of these pieces that is the information that it already told us. It told us sine of beta, and it told us cosine of alpha. So I could even go ahead and plug those in. I know that this is 3/4, and I know that cosine of alpha is 1/2. So what's left to figure out is sine of alpha and cosine of beta. So in order to figure out what these are supposed to be, we have a couple of options. One, we have our Pythagorean identity, that sine squared plus cosine squared is equal to 1. So I could say, well, if sine is 3/4, then 3/4 squared plus cosine of beta squared is equal to 1, and solve for cosine there. Now, you're absolutely, that erased way too much. You're absolutely able to do that, but I think the approach may be a bit quicker if we instead draw a right triangle for that instead. So what I mean by that is that I know sine of beta is 3/4, but I also know that my SOHCAHTOA rules have to always hold for any angle in a right triangle. So if I draw this right triangle and I call this angle here beta, then I know that sine of beta has to be equal to opposite over hypotenuse. So 3/4 is equal to opposite over hypotenuse. So 3 and 4. Well, now, if I want to know cosine of beta, because of this part, then I want to know cosine in this triangle. Well, we know that cosine is adjacent over hypotenuse, so that tells me that all I need to do is figure out what this missing side length is. Well, we have our Pythagorean theorem. That's a squared plus b squared is equal to c squared, which in this case would be something like a squared plus 3 squared is equal to 4 squared. But 3 is 9 and 4 is 16. So a squared is equal to 16 minus 9 is 7. So a is just the square root of 7, which means that cosine would need to be this ratio, the square root of 7. Let's see if I can erase only a specific part. Okay. I'll never understand the Zoom eraser, what it decides to erase. So, sorry. Cosine of beta right here should evaluate to the square root of 7 over 4. But something that we ignored here was in our right triangle, all of our side lengths are positive. So if cosine was supposed to evaluate to be some negative value, right, if we're supposed to be in quadrant 3, then I wouldn't know that because all of the sides of my triangle were just written down to be positive. So really, if you look into the worksheet for this kind of question, it actually tells us exactly what quadrant alpha and beta are in, which is what we'd want to refer to in this question. Now, if you don't have that kind of information, if it doesn't tell you, just kind of see what information you can guess. And in this case, I really didn't tell you enough information. So we're just going to pretend that we know it's positive. But technically, I'm just kind of making that assumption. So anyway, this is the square root of 7 over 4. Really, we want to check if it's positive or negative, but I'm not going to do that here. Then we still need to figure out what is sine of alpha. Well, that needs to come from cosine of alpha, which again, we could choose to do sine squared plus cosine squared is equal to 1, but instead, we're going to do the same work, but maybe a little bit quicker to instead draw this triangle and say that, well, if cosine of alpha is 1/2, then adjacent over hypotenuse is 1/2. So 1 over 2. Now we have 1 squared plus b squared is equal to 2 squared. So 1 plus b squared is equal to 4. So b squared is equal to 3. So b must be just the square root of 3. Well, since I need sine of alpha, that should be the opposite over hypotenuse. So the square root of 3 over 2. And that's our answer. This huge, well, not huge, this sum with a lot of pieces. So as much as it feels like there's a lot going on, ultimately, there isn't too much crazy happening. It's just a few of the ideas that we should be okay about, solving for sine or cosine, given only the opposite one. AKA, I would give you cosine, can you find sine? I give you sine, can you find cosine? And that's just comes from these triangles here. Now, you may remember on a previous quiz that you were asked to do this kind of question, and the instructions said don't use any right triangles. That was just so that we knew that you knew this identity, sine squared plus cosine squared is 1. But now that that's not really what we're testing over, feel free to draw these right triangles. And in fact, as you can kind of tell by what I did here, I kind of encourage it because I do think it saves time, and maybe is a bit more clear and easy than trying to do all the squaring of fractions and all that mess. Yeah, okay. So the last thing that I actually want to talk about is actually, instead of doing a whole nother problem, I'm just going to emphasize something from the last exercise that we did in 9. And that was the thing that was, sorry, that was the part that asked for something that looked maybe a little bit intimidating, and I'll draw a line to show this is a separate question. It asked for something like sine of cosine inverse of 1/2 minus tangent inverse of 6/7, which at face value looks weird and maybe intimidating. But if we look at these and the individual pieces that they came from, it's no different than the previous question. It is no different than the previous question. Okay, so all I'm going to do to help us maybe see this is I remember my inverse function here, cosine inverse of 1/2, just gives me the angle. This is just going to be some angle that I'm going to call alpha. Specifically, that is the angle alpha, where cosine of alpha is 1/2. That's all cosine inverse is. Some angle where cosine of that angle is 1/2. And similarly, tangent inverse of 6/7, I can call beta, where that is just the angle where tangent of beta is 6/7. So as we can kind of see, all that it's really asking, once I just replace these variables, is it wants sine of alpha minus beta, where cosine of alpha is 1/2 and tangent of beta is 6/7. Now, this is exactly like the previous question, except it's just worded with inverse functions where we assume the domain instead of just starting up over here where I tell you cosine of alpha is 1/2 and alpha's in this specific quadrant. Instead, we know the kind of range that our inverse function should land us. And that should make everything work nicely from there. Okay. So again, this setup immediately becomes the same as the last question, where I use my angle difference formula and know that this needs to be sine of alpha cosine of beta minus cosine of alpha sine of beta. Then, well, now I know cosine of alpha should be 1/2. But that's really all I know right now. But again, if cosine of alpha is 1/2, then we can draw this right triangle for alpha. And cosine is adjacent over hypotenuse. So since that's 1/2, I do a 1 here and a 2 there. And then I figure out this side, and then I figure out what sine of alpha is supposed to be from that. Well, then for this triangle with beta, if beta is this angle, I know that opposite over adjacent is 6/7. So I'll call this 6 and I'll call this 7. And then I just figure out what the hypotenuse is here. And then I can do cosine of beta as adjacent over hypotenuse and sine of beta as opposite over hypotenuse. So again, this question ends up being almost the same as the previous up here. It's just that the information they give to you is phrased differently. So very good. That's all that I have for right now. Yeah, I'm not doing any outro. Goodbye.